Elementary series, really what elementary series are a bunch of series that you're going to have to know by sort of memorization, by heart, just recognizing what function it is. We've talked about e to the x, what that looks like as a Taylor polynomial. We've talked about cosine x, what that looks like as a Taylor polynomial. Now we're going to talk about two others. Actually, we've talked about the natural log, I think, too. So anyway, that's kind of what the deal is for, what you have to know, okay? And get used to seeing page 206 is where we're going to start, but there's nothing on there. I'm going to give them to you. I probably should have given you e to the x and cosine x first, but I'm just going to go in order of this, okay? We kind of touched on it a little bit when I showed you that video, but the sine of x, the key thing here is it starts with the x term, and I included the general term too, okay, because the general term seems like that's tripping you up more than anything. But this is the odd powers and the odd factorial. So x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th, and it goes on forever, of course. So the sine is the odd values, okay, the odd powers. And then the cosine was the even ones, and it starts with 1. But notice that they both alternate. 1 plus, 1 minus, but they both start with plus. Okay, they both start with a positive term, so it goes positive, minus, etc. But the cosine is the even ones. And like I said, we've talked about the cosine one, briefly touched on the sine one, but notice in each of the general terms we have this -1 to the n, and we talked about that last week too. That's sort of your indicator that the series is going to alternate signs. The e to the x, we've looked at that one, and that was x to the n over n factorial. And so that was always addition. The first term is x over 1 factorial, x squared over 2 factorial, so that all lined up. That was the first one I showed you because it's basically the easiest one. If I recall, I think we originally started with like natural log of 1 minus x, and then we subbed in, and that's what we ended up having an x minus 1 in there. And so we did talk about this one too. This one, oh, that needs to be gone. There we go, that's better. So this one almost looks like the e to the x, but it's an x minus 1 instead of and it doesn't have any of the factorial. So no, I guess it doesn't really look like e to the x at all. But it follows that the squared over 2, the 3 over 3, and there's no factorial. And there's no first term of the 1. So, I mean, there's similarities across the board on all these, right? Like the sine and cosine almost seem complementary to each other. It's like all the terms that are missing from cosine are in sine, and all the terms that are missing from sine are cosine, except for the position of the plus and minus. The natural log one is actually, I would separate that one out from the other ones because it doesn't have the factorial at all. But you have to know these, okay? I know we've talked about them a little bit, but this is something, and you need to figure out what way is going to work best for you to memorize that. Obviously, we know there's a relationship between sine and cosine. There's a relationship between e and natural log. So it probably makes sense to kind of think of these together and think of these together and come up with your way to memorize. So these are the 3 examples, I think, in the book. And it essentially is asking you to create a new power series based on those elementary series using, these, sine of x squared. Obviously, the relationship is going to be to sine of x. Cosine of the square root of x, the relationship is going to be to the cosine function. And then x times e to the x, of course, that's going to be with the e to the x function. And so, like I said, I'm not going to actually do these, but just so you're clear what you would do for this first one. I mean, do you guys have a thought about what you would do here? How about that? What would I do with the elementary series to find this?
Plug in x squared for x.
Exactly. That's it. Plug in x squared for x in the elementary series for sine x. And then, so all the numbers are the same other than the powers on x. Everything else is the same. So you'll get some practice. This is the thing that, memorizing these things will become easier because you're going to get practice doing that. All right? So, of course, then what am I going to do for the cosine of the square root of x? I'm sorry? Loud.
Plug in x to the 1/2.
X to the 1/2. Oh, there we go. I was like, plug in x. What are you talking about? Just plug in square root of x. Yeah. Either one. X to the 1/2, square root of x. However you want to do that. It probably makes more sense to make it x to the 1/2 because you're going to be squaring it and, well, let's see, cosine. Yeah, so you're going to raise everything to even powers. So that probably work. How about the last one?
Multiply everything.
Yeah, that's it. Multiply everything by x. So the idea behind the elementary series is it's your sort of foundation, it's your starting point. But then we can expand from there and come up with new power series. So right, in this, instead of just writing x times the thing, you actually would multiply it out. Our whole goal is, I guess, even putting the x with the parentheses gives us a new power series, but one of the things that you are probably going to be asked to do is come up with a general term, and if you don't already know the general term, you can generate it that way. But for those four, you should really get in the habit of knowing that general term, especially because I know that is the challenging thing for you. So work on the thing that's a little more challenging. All right. This one's tricky, so I want to go through it. Okay. This is the example number 4. So we're going to create a power series from 1 over x. Now, your first thought when you see 1 over x, hopefully, is a relationship to what? To the natural log. What about the natural log? What about the natural log? Derivative of the natural log. That's where we want to go. So when you see that 1 over x, you should be thinking about how it's related to the derivative of the natural log. And then what we're going to do, since we know what the natural log elementary series is, right? We talked about that on the previous page, and we actually derived it. What we're really doing is taking the derivative of that. That's what 1 over x equals as an elementary, or as a power series. And so what you end up having to do is just differentiate that. And that will give us 1 over x. So I want to give you a few minutes to try to do that, including differentiating the general term. So do that. So as you started going through this and differentiating this, of course, this is a 1. The 2 comes down, right? And then what happens? It cancels out, okay? And so we're going to see that that just keeps happening. Right? And then let's talk about the derivative of the general term, because I think we've had some issues with that. This is just a constant, okay? So we just kind of ignore that since we have a variable involved. So I'm going to have, this is still going to be here. When I bring this down, and this just becomes n minus 1, it still cancels. Okay, so this piece takes care of the changing signs, and then this gives me my my variable term. Okay, and so what you had, again, I gotta get rid of that. Come on. Something like that. Okay? And you could actually figure this out without differentiating this term if you find the pattern. But you can differentiate the term, and that will help you figure out the pattern as well. Okay? Questions on that? Okay, we got to go one more. We got one more with this elementary, so we'll kind of move on from that. So we've differentiated. Now we're going to integrate. So in this case, we're going to integrate from 1 to t of the natural log of x. And here's really what we're doing. Okay? We are going to integrate that power series. Because again, we're trying to create a new power series. Those of you who are wondering, well, why can't we just straight up integrate it? Well, because the whole point is we're working with power series, and that's what the directions ask us to create a new power series. Okay? So again, that's the natural log elementary series. And then we have to integrate it. Let's go ahead and give that a try. Questions about where that came from? So I didn't simplify. Here's the thing. If you notice here, I didn't simplify these denominators, right? So this, obviously, we increase it and then divide it by 2, increase it, divide it by 3, increase it, divide it by 4. And that helps us start to see the pattern. Now, at the same time, when you go to integrate this, I still have my negative 1 to the n minus 1. Okay, this goes to x minus 1 to the n plus 1, and then I have my n plus 1 on the bottom. So this, integrating this general term, also reflects the same kind of pattern, okay? The thing that's nice when I go to actually determine what the integral is when I plug 1 in, these all become zeros. So subtracting a big fat 0 off of this, it really just is a matter of plugging t in for x, and that's kind of where we land, okay? You could simplify this at this point if you wanted to, but there's really no need. You could just leave it like that. But that's where we come up with that, how to integrate a power series and generating a new power series. So oftentimes what you should be thinking when you see some of these problems is when it's shifted a little bit from what the normal elementary series is, be thinking that there might be a relationship between the integral or the derivative of it, and maybe that's where it comes from. Okay? All right, let's shift to the alternating series test. I mean, we're going to talk about what an alternating series is. We've been talking about it already, right? We've been talking about it for a few days. Alternating series just means the terms alternate between positive and negative. And that negative 1 to the n minus 1 to the n plus 1, that's your indicator that it's an alternating series. And as we talked about earlier, 3 of the 4 elementary series were alternating. The only one that wasn't was e to the x. Okay. And so we're going to have a new test. So far we have 2 tests. We have the geometric series test, which tests for convergence and also tests for divergence. We have the nth term test, which only tests for divergence. Okay. It does not test for convergence. Only for divergence. Now we're going to have a new test, okay? That is the alternating series test. And this is a test for convergence. So now we have 3 tests, 2 for convergence, 2 for divergence. Geometric series test tests for both. Nth term test tests for divergence. Alternating series test tests for convergence, okay? And we have like 3 more tests. So after this, all right. So here are the conditions. And the reason that they wrote both of these, right? That's if there's a shift, if you want the first term to be positive, if you want the first term to be negative. That's the only difference between these two, okay? Here are the conditions that have to exist in order for you to be able to use the alternating series test. Off, the terms have to alternate. Okay. And when if you choose to use the alternating series test, okay, you got to state these things. Make sure the conditions exist and state them. You know, the other thing I was thinking about in terms of the order in which you want to try this, I would always try the nth term test first, right away, because that's pretty easy. Find the limit. Does it equal 0? Okay, then we got to try a different test. It's not equal. It doesn't equal 0. It diverges. Done. Move on. Like, there's not a lot to actually do. You don't have to prove conditions and all that stuff and state conditions. You can quickly find the limit and show that it doesn't equal 0, and then you're like, it diverges. Great. Move on. So to me, I would check that one first. Anyway, that's not the point for this, but I'm just thinking big picture strategy, because eventually they're just going to give you a series and say, okay, does it diverge or converge? And then you have to state why. You might as well see if you can get it to diverge with an easy one and then be done and move on. All right, next piece. Okay. A sub n plus 1 is less than or equal to a sub n for all n after a certain n. Okay, what that means is, like, the first couple terms it might not work for that. But like for the third, fourth, and on down, this will work, okay? And let's understand what this really means. This is the term we're at, and this is the succeeding term, which means, what's another way to say what this is, like in English? It's getting smaller, right? The terms are decreasing. There we go. Okay. So all that is saying is that the terms are decreasing. Okay? Each individual term, as you compare them, as you move along the series itself, those terms are getting smaller. And the piece that after a certain end, it could happen from the first term. It can decrease right from first term, second term, third term. It might not start decreasing until the fifth term, but then it decreases from 5 to infinity. Okay? And so if something like that happens, you state that. Okay? It meets the condition when n is greater than or equal to 5, or something like that. Yeah. What we're saying here, because once we determine that it alternates, then we kind of ignore the signs. What we're talking about here is these terms are decreasing without consideration for what the sign is, right? Because if we always consider the sign, it'd be like, oh, it's a positive, then it went down to a negative, oh, it went back up to a positive, and it starts doing this oscillating thing. Well, for the alternating series test, we don't concern ourselves with the sign anymore. We're talking just about the absolute value of the terms at that point, or just disregard the sign, however you want to think about it. Okay? So there's the first two conditions. And then the last condition is that the limit equals 0. If all three of those things occur, then we can use this test, and we know that this series converges. It doesn't tell us what it converges to. It just tells us that it converges. And there's other ways that we're going to look into that. Okay. All right, cool. I'm going to go. We've got 2 examples to go through. 5 minutes. See if we can do it. Okay. Now, these are examples 6 and 7. All right. Clearly, we have alternating. This is my alternating, right? This -1 to the n plus 1, -1 to the n plus 1. That indicates that our series is alternating. Okay. The terms are decreasing. Think about it. 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. So when the denominator gets bigger, the whole thing gets smaller. And then, of course, the limit of 1 over n equals 0 as we approach infinity. Okay? And it's of the terms. It's not of the series, right? The terms are approaching zero. We're not saying that the sum is approaching zero. We're saying each of the individual terms are approaching zero. Okay, so all three conditions are met, which means we can say that it converges by the alternating series test. And so, again, I got in the habit of it. It's a bad habit. Write it out. Write the name of the test out. Sometimes when I screenshot from the answer key that I have, like he doesn't ever write it out. He'll put AST. You saw GST or NTT. Like that's a bad idea. I feel like that's just going to get you in trouble on the exam. Okay. Question.
Everything, the conditions.
You can if you want, but usually especially for the decreasing part, if you can't just do it in your head when the terms get kind of, I don't know, more complex, you might want to write a few of them out just for your own, because if they aren't decreasing, then yeah, you can't even use this test. Okay. All right, for the next one, we'll go through this one a little bit slower. It is alternating. Okay, it's alternating because of this. Is it decreasing? So if I plug 1 in, I get 2 over 1. Plug 2 in, I get 3 over 2. All right. So it went from 2 to 1.5. Then I plug 3 in, I get 4/3. So 1.3 from 1.5. Yeah, it seems like it's decreasing, so we're good there. Okay, terms are decreasing. What is the limit of this thing? What is the limit approaching? Limit of n plus 1 over n. 1. Okay. Now, the alternating series test is for convergence. So I cannot just say it diverges. Okay. What we say is that it's inconclusive. And if I want to show that it converges another way, you could look into that. The only other one we have is a geometric series test, which that this is not. But then you go to nth term test. Okay? Since we've already found the limit, okay, it doesn't equal 0. Therefore, it actually diverges by the nth term test. In fact, if we weren't working on alternating series, I would have, like I was saying earlier, I would have done the nth term test right away. And said, all right, the limit doesn't equal 0, boom, diverges, nth term test. Don't even mess with the alternating series. Okay. At the same time, the alternating series takes out the plus minus issue. Okay. The nth term test doesn't, but it still approaches 0 either way. Okay, so here's kind of a summary. I think this is kind of good to have. This is what I was talking about earlier. But here's what we have so far, okay? Nth term test for divergence. It's at the top because I would always check that first, like I was saying. Then you have geometric series for divergence or convergence. And then now we have alternating series test for convergence, okay? So that's what we have so far. Like I said, we're going to get 3 or 4 more. I can't remember off the top of my head. Direct comparison, limit, ratio. Maybe it's only 3. Okay. This part of the workbook I think is helpful because now we're starting to, it's sort of like factoring when you first learned how to factor, right? You had to go, all right, can I try? Did the conditions exist for me to use greatest common factor? Oh, I can always use greatest common factor. Sort of like the nth term test. I have to have a trinomial in order to do it that way. Okay, that's like some of the other ones. It's kind of like that. You have this whole list now in your head of ways to factor. What we're coming up with is what we're developing is the list to determine convergence and divergence. And this is where we're at right now.